Section 3.2, Measures of Dispersion. In this section, we'll look at these 5 objectives. Before we begin, we're going to look at an example. To order food at a McDonald's restaurant, one must choose from multiple lines, while at Wendy's restaurant, one enters a single line. The following data we'll see on the next slide represent the wait time in minutes in line for a simple random sample of 30 customers at each restaurant during the lunch hour. For each sample, we want to answer the following. What was the mean wait time? We'll draw a histogram of each restaurant's wait time, and then we'll look at which restaurant's wait time appears more dispersed. Which line would you prefer to wait in and why? So here we see the data for the wait time at Wendy's and the wait time at McDonald's for our 30 individuals. When we calculate the mean, we notice that we have the same value. The mean wait time in each line is 1.39 minutes. So here we see the histograms drawn out for the wait time at Wendy's and the wait time at McDonald's. Notice that both have the same wait time, but the histograms indicate the wait times for McDonald's are more spread out or more dispersed. So while the wait time of 1.39 minutes is typical at both, it appears to be more reliable at Wendy's. So that is, there's a higher proportion of wait times within a few seconds of the average at Wendy's than there are at McDonald's. So to answer our question for part C, I would probably prefer to wait in line at Wendy's, since I'm more likely to be waited on in a timely manner there. Objective 1, we want to determine the range of a variable from raw data. The range, given by a capital R, of a variable is the difference between the largest data value and the smallest data values. That is, the range, or capital R, is our largest data value minus the smallest data value. So let's look at an example. The following data represent the travel times in minutes to work for our 7 employees from our startup web development company, and we want to find the range. So the first thing we do is we locate the largest data value, which we see is 43, and we locate our smallest data value, which is 5. So the range, R, is going to be our largest data value, 43, minus the smallest data value, 5. And we see that we have a range then of 38 minutes for our company. Objective 2, we want to determine the standard deviation of a variable from raw data. The population standard deviation of a variable is the square root of the sum of squared deviations about the population mean divided by the number of observations in the population, capital N. That is, it is the square root of the mean of the squared deviations about the population mean. And it is symbolically represented by our lowercase Greek letter sigma. Kind of looks like an O with a line on top. Here we see the formula for our population standard deviation, where our x values are our observations. There were a total of n of them, since it's a population, and mu is the population mean. A formula that's equivalent to the one on the previous slide is called the computational formula for determining the population standard deviation, and it's given here. So we'll see how we can use these different formulas to find our standard deviation. So let's go back to our example of our startup web development company, and we want to compute the population standard deviation of this data. The first step is we find mu, and we've already done that on the calculator, and we know that our mean value was 24.85714. So we'll take it out to about 5 decimal places. And we're going to make our table here. So we've listed the data values, and the next step we're going to list the population mean. In our next column, we want to take each data value and subtract the population mean. So here we'll take 23 minus the 24.85714. And the next step, we'll take 36 minus that value as well. And we continue that so on until we obtain all the values in that column. The next column, we want to take each of those values and square them. And notice that when we square them, they'll all become positive. So as part of our formula, we want to sum the values in our last column here. When we sum that last column, we see that we get approximately 902.8571. And our population standard deviation, using the formula, we see that we have the sum of our last column divided by the total number of observations. So remember that the sum of our last column was our 902.8571. We'll divide that by 7. And then lastly take the square root. And we see then that we get approximately, and that's what the squiggle is because I'm rounding, we get approximately 11.36 minutes for our population standard deviation. And that was using the original formula. Now let's use the computational formula and see that we get the same answer. We take each of the observations and we square them in our next column. Then we sum each of those columns. And we'll take the sum of our first column minus the sum of the second column divided by the number of observations. That's the top part of the formula. Then we'll divide that by our number of observations, 7. And we see that we get exactly the same amount, which is 11.36 minutes. So you can use either formula you like. The sample standard deviation, indicated by a lowercase s, of our variable is the square root of the sum of squared deviations about the sample mean divided by little n minus 1, where our little n is the sample size. And here we see that formula given. Just like we did for the population standard deviation, we also have a computational formula for the sample standard deviation. And here we see it now. We call n-1 the degrees of freedom because the first n-1 observations have freedom to be whatever value they wish, but the nth value has no freedom. It must be whatever value forces the sum of the deviations about the mean to equal 0. So in this example, we want to compute a sample standard deviation. And this is the results of our first random sample taken from our travel times for our 7 employees in the startup web company. And we see these 3 here. And we want to find the sample standard deviation of those. So again, we make a table and we find the sample mean of those, which was 22.3 repeating. We'll take each value minus that mean value for our next column, and then we'll square that column and take the sum of it. And we see that that sum is 500.6 repeating. So our sample standard deviation will take that sum under the square root sign and divide that by n-1. So instead of 3, we're dividing by 2. We get approximately 15.82 minutes. We'll see that using the computational formula, we get the same result. So we list our 3 values and we square them in our 2 columns here, and then we sum both of them. And we see that our sample standard deviation, S, is then equal to the sum of our second column minus the sum of our first column divided by n, and then we divide the total by n-1 and take the square root. And we see we also get 15.82 minutes. So let's look at an example where we compare standard deviations. We want to determine the standard deviation waiting time for Wendy's and McDonald's, then look at which is larger and why. So here's our data set for each one that we looked at the beginning. And we're going to look at finding these values on our calculator using technology. The first step is to enter the raw data in list 1 by pressing Stat and selecting 1 for edit. So we'll press Stat and enter. I'm going to arrow up to L1 and hit Clear to empty the list. And then I'll hit Enter, and you'll notice the list is cleared. So let's look at our sample standard deviation from our previous example, and we'll enter our 3 values here. The next step is to press Stat, arrow over to Calc, and hit Enter on one variable stats. With our one variable stats on the home screen, we'll press Enter, and we see here, we looked at this earlier for the mean, but we see now that we have Sx is our sample standard deviation, which we found previously to be 15.82. Notice under it we see a population standard deviation given, and that value is a little different. And if you remember, the formula was a little different. We're dividing by a different number. So let's go back and hit Enter, Stat and Enter. And we'll enter the values from before that. And remember, we had 7 data values. We hit Stat, go to Calc, hit Enter, and then hit Enter again to do it. And we see now that we get, for our population standard deviation, that we had about 11.36, which is what we found using the formula. So this is a much faster way to find our population and our sample standard deviation. The key here is to make sure you're using the right value. So pay attention to the wording and the variable that's used. So if we look at the data values for Wendy's and we enter them all into a list in our calculator, we can easily find that the standard deviation for Wendy's is 0.738 minutes. And the sample standard deviation for McDonald's is 1.265 minutes. And recall from earlier that the data is more dispersed for McDonald's, which results in a larger standard deviation. So that's what we would have expected. Objective 3, we want to determine the variance of a variable from raw data. The variance of a variable is the square of the standard deviation. So the population variance is sigma squared, and the sample variance is s squared. So looking back at our startup company with our 7 employees, we want to compute the population and sample variance of this data. Recall that the population standard deviation is 11.36. So the population variance is going to be sigma squared, or 11.36 squared, which is approximately 129.05 minutes. So we see on our calculator that our population standard deviation is displayed. Now I would recommend that when you're using a calculator to square your value that you take it out about 5 decimal places. So we'll go ahead and type in 11.35691 and hit the squared key and then hit Enter. And we see that we get a slightly different value. So when you're doing your homework on the computer, you will want to make sure you're taking out about 5 decimal places in order to avoid getting an error. If we had just done it the way we have it on the screen, 11.36, and square that, then we see that we get the value we had there, which was 129.05 rounded. And the sample standard deviation is s equals 15.82, so our sample variance is s squared, or 15.82 squared, which is approximately 250.27 minutes. And again, the same thing applies when you're using the calculator on the sample standard deviation. and variance. You'll also want to take the sample standard deviation out about 5 decimal places when you're inputting your answers in order to avoid an error. Objective 4, we want to use the empirical rule to describe data that are bell-shaped. The empirical rule says if a distribution is roughly bell-shaped, then approximately 68% of the data will lie within 1 standard deviation of the mean. That is, approximately 68% of the data lie between the mean minus a standard deviation and the mean plus a standard deviation. Approximately 95% of the data will lie within 2 standard deviation of the mean. So approximately 95% is between the mean minus 2 standard deviations and the mean plus 2 standard deviations. And then approximately 99.7% of the data will lie within 3 standard deviations of the mean. Take note that we can also use the empirical rule based on sample data with x bar used in place of mu and s used in place of sigma. And here we see a picture of that. And notice the 68%, 95%, and 99.7% are labeled. Those are 3 values you'll want to make sure to remember. So let's look at an example. We want to use the empirical rule. From data representing the serum HDL cholesterol of the 54 female patients of a family doctor, we found a mean of 57.4 and a standard deviation of 11.7. So the first thing we want to do is determine the percentage of all patients that have serum HDL between 45.7 and 69.1 according to the empirical rule. So the first thing we're going to do is draw a picture. We're going to put our mean value in the middle, which was 57.4. Then we want to take 3 values on either side. And going this way, we're going to add a standard deviation each time. So we add 11.7 and we get 69.1. We'll add it again and we get 80.8. We add it again and we get 92.5. And going this direction, we want to subtract a standard deviation from our mean. So the first value we have is 45.7 when we subtract our 11.7. Then we get 34.0 and lastly 22.3. So now we label, according to the empirical rule, we know that within 1 standard deviation on either side is 68% of our values. Within 2 is 95%, and within 3 we have 99.7%. So notice we're looking between 45.7 and 69.1. Notice that those values are here. So then we see that according to the empirical rule, that 68% of all patients will have our serum HDL level between that, which is within 1 standard deviation of the mean. Next, we want to determine the percentage of all patients that have a serum HDL of less than 34 and greater than 80.8 according to the empirical rule. So we redraw our picture here. We're looking at less than 34. So I'm going to draw this on here. We want less than 34 and we want greater than 80.8. So you need to remember that the entire curve here is 100%. So in order to find the area in the 2 tails that we have here, we're going to subtract this middle value here, which we see was our 95%. So we want to take 100 minus the 95, and we'll end up with 5% being the percentage of our patients that have the serum HDL less than 34 and greater than 80.8. So that's in both of those tails. Now we want to determine the percentage of all patients that have a serum HDL greater than 80.8 according to the empirical rule. So we have our picture here again, and don't mind the percentages in the middle. But remember, we still have our 68%, 95%, and our 99.7%. So we're looking at only greater than our 80.8. So notice that the 80.8 links up here with the 34.0, and that's our 95%. So we're going to follow the same step like we found in part B and take 100 minus the 95, and we get 5%. So that, though, however, is both tails like we found in part B. So to find the area only in this one tail, we're going to divide it in half, remembering that the curve is symmetric. So when we divide it in half, we see that we get approximately 2.5% of our patients that have a serum HDL greater than 80.8 according to the empirical rule. In Objective 5, we want to use Chebyshev's inequality to describe any set of data. Chebyshev's inequality says that for any data set or distribution, at least 1 minus 1 over k squared times 100% of the observations will lie within k standard deviations of the mean, where k is any number greater than 1. We can also use Chebyshev's inequality based on sample data. Let's look at an example. We want to recall that from the serum HDL cholesterol of our 54 female patients of a family doctor, we found a mean of 57.4 and a standard deviation of 11.7. So we'll use Chebyshev's theorem to first determine the percentage of patients that have a serum HDL within 3 standard deviations of the mean. So 3 standard deviations means that our value for k is 3. So we want to take our formula, which is 1 minus 1 over k squared times 100%, and we'll replace k then with the value of 3. And when we work this out, we'll get approximately 88.9% according to Chebyshev's theorem. Next, we want to determine the minimum percentage of patients that have a serum HDL between 34 and 80.8. So what we have to do here is find out how many standard deviations away from the mean each of those are. And they're going to be the same amount away, so we're going to really look at just one of them. So we'll take 80.8 and we'll subtract the mean from it. And then we'll divide that by the standard deviation. So we get 23.4 divided by 11.7. So we see that we have 2 standard deviations. So our value for k then is 2. So now we can use Chebyshev's theorem and take 1 minus 1 over 2 squared times 100%, which will be 75%. So the minimum percentage of patients that have our serum HDL between 34 and 80.8 is 75%, according to Chebyshev's.